Hello and welcome to today's IWCS webinar. My name is Connie and I'll be your Cisco producer for today's event. Now, I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. Feel free to post your questions during the presentation. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Wayne Kachmar, President, Technical Horsepower Consulting in Vermont in the USA, who will be presenting his paper on evaluation of fiber optic ripcord designs and use procedures. Wayne Kachmar is president of Technical Horsepower Consulting, LLC, which provides technical support related to design and processing optical cable. He is a 39-year veteran of the optical cable industry. During that time, he has developed many unique cable designs for many specialized applications, including optical sensor cables embedded in the Antarctic ice pack, flight critical aerospace cables, medical laser transport cables, and numerous military applications. During his career, he has participated in many standards bodies, including EIA, NJATA, NECA, and SMPTE to help create cable and connector test methods. In 1988, Wayne founded Northern Lights Cable Incorporated, which was acquired by progressively larger cable and connectivity companies, most recently TE Connectivity. Mr. Kachmar retired from TE Connectivity as a fellow in electro-optic engineering, their highest technical role. Mr. Kachmar is the inventor on more than 50 patents in fiber optic product designs and technologies. He holds an AAS degree in electrical technology from the State University of New York. Wayne, we welcome you to present at today's IWCS webinar series event.
Thank you. And I think I am all set to start here. So this paper is on how to evaluate fiber optic ripcord designs and use procedures. So, of course, the first question that you would have on that would be, there it goes, what is this paper really about? I mean, we've had ripcords around for decades, and we're talking about an item that's just generally added to a product. You know, copper and fiber cables have had ripcords, and aren't they pretty much the same product? And actually, are we just adding a ripcord to a product? And really, the other part of this is, what do we actually have to tell the installer about ripcords? When we talk about this, we talk about the fact that a lot of people are using ripcords and assume that they are the same regardless of what product they're on, or that what they've used in the past works the same way. So what we're going to cover is there's an array of different types of ripcords or ripcord activities that are in use today. Another big area is how effective are they? Are some of these ripcords nothing more than complying with a standard? And in some cases, maybe they are there, but without knowing the proper procedures, they don't seem to work. Which brings us to the issue: are the existing tests for ripcords and the procedures that are promulgated to use them an accurate reflection of this? Do they actually show that the ripcord will perform or do its job? And the real question is, where are we going in the future? Why does this matter? How do we use them? To a great extent, are they becoming more important because of the products and the way we're using our products today, or the way we're designing cables? Think about the fact that first fiber optic cables that were high density were 24, 48 fibers. Today, we're discussing 3,000, 4,000 fiber cables. Just the sheer volume alone that changes it, changes how we perceive what we have to do to get to that cable. And so then the question becomes, what's so important about ripcords? Why do we even care? Well, there's several things. In our industry, we've had to reduce the cost. If you look at our curve of fiber cables, fiber optic cables have followed the semiconductor curve. In the early 1960s, the cost of a transistor was somewhere around $6. By this year, with the cost of a PNP junction is somewhere in the hundredths of a cent on an integrated circuit chip. And if you follow that curve, it's the traditional drop-off where the prices drop fairly significantly over a short period of time, and then the tail gets very long. We are in the same situation with fiber cable. And now our cost per foot is so critical that we are looking to save money at every potential item. In the very beginning, the cost of an optical fiber was 20, 30, 40 cents a meter for the bare glass. If you put 48 fibers in there at, let's say, 25 cents a meter, you had $12 of fiber. So saving a penny a meter on the ripcord didn't matter. In fact, it just was lost in the noise. However, when you're looking at prices of fiber that are under a penny a meter now, saving a half a cent a meter on a ripcord becomes a significant cost reduction. And so that's some of the changes that we see today. Even saving a tenth of a cent, sometimes we may give up practicality and reliability for cost savings. The other thing is, as we have higher fiber count cables, they're stripped over much longer lengths. Fiber optic cables typically are not stripped only over a half a meter, but many times 5 meters, 6 meters for splicing, for distribution within a frame. Many different applications are requiring that jacket to be removed. And again, ripcords for copper cables and mechanical cables are very different than ripcords for fiber optic cables. Our cores are generally not mechanically strong. Normally we buffer rather than we insulate. We build, if you will. There is no strong core. Our strength in many cases is right under that jacket. And in some cases, we perceive it's nothing more than a piece of yarn someone grabs to just quickly peel the jacket off. And a short history, though, brings us back to why we do this. Early cables, as you'll see in the picture here, used a braided design. And that braid, if I can point this out here, was a loose series of yarns that were actually put over soft jackets, and you could literally push this yarn back. It would bundle up and get, like a Kellam's grip, would get larger in diameter. You could then just take a scissor and cut it, and it went away. You never touched the core. And so, therefore, it was no longer a big issue. But for the later cables that started to use extruded jackets, the fillers in various flexible cables became an ad hoc ripcord. People were actually pulling the fillers that were yarns, or in some cases, literally cotton threads, and trying to tear through jackets. And for short distances, it might have worked. Now, along comes fiber optic cable. It looks like copper. It almost seems like it's generally a copper type of design, but it's not. Fiber optic cables have a very soft core. They generally do not have mechanical strength. The conductors in electrical cables are the mechanical strength items in the cable. While you may have other strengthening agents such as a wire braid, in general, the conductors of a insulated or bundled copper cable were mechanically strong and provided the rigidity that a simple ripcord could use. And of course, our industry, the wire industry as a whole, not just fiber optics, is somewhat resistant to change installation procedures. And you'll hear me talk quite a bit through this presentation about tribal knowledge. I define tribal knowledge as the information that is passed from journeyman or master electrician or installer or technician to the apprentice technician. Not necessarily the information that was learned in schools. To a great extent, tribal knowledge in that field has always been that you just yank on the ripcord, and if it breaks, don't worry about it. You can slit it with your knife. So we talk a little bit about that on a regular basis. And I think that at this point, fiber optic cables, we talk about the differences. The normal methods of end cable prep. We'll start with cutting or skinning a short length of cable to expose the ripcord. And we typically would, in our designs, prep that end by, in the copper world, using a knife, skinning it, but in fiber, pulling that length off by ringing it and looking for a short piece of ripcord. And that's the typical method that occurs, but we have to strip much longer length. We isolate the optical fibers from the outside world. And for many years, we used thixotropic gels, which would protect the optical fiber waveguides from all outside layers of the cable. We used to refer to that as a fiber womb, W-O-M-B, because of the fact that the glass fibers were literally contained in a semi-viscous environment that protected them from moisture, air, oxygen, what have you. And when we make indoor cables that don't use gels, they have lots of open spaces in those cable designs. And those open spaces are a bigger problem, if you will, going forward, because we know that those spaces are soft and they can absorb moisture, but they also are allowing us the flexibility to handle a fiber cable. You'll see in some of the pictures over here that there are a number of different designs that are indoor cables shown here. And now we are going on high fiber count cables to a number of central tube designs, which is this item down here, where you basically have a large tube and bundles of ribbons or loose fibers bundled up inside it. There's not a great deal of strength here, so when you're peeling on the jacket, you have the ability to kink these cables very easily. And a kinking of the cable is a significant problem. So, again, we're stripping fibers for much longer lengths. Today, it's 1 to 5 meters are typical. On a high fiber count cable, that may actually be short. In some cases, we're stripping it to put the fibers and the tubes that they're in inside a splice case, and then stripping the tubes off for the individual fibers to be used in a fusion splicer or a mechanical splice application. In other cases, we are taking the fibers and breaking them out into individual frication tubes to put single fiber connectors on them, or breaking out a bundle of fibers or a ribbon to put into a 12, 24 fiber connector, such as an NP, and so forth. So we have to strip longer lengths for access. We can't afford to damage that core in the process. So we have to leave the intrinsic mechanical protection intact, Now, in an optical fiber, most of you know that's referred to the fiber coating. In some cases, it may include a tight buffer, which is a directly contacted material between 500 and 900 microns in diameter, or in some cases, a group of fibers, maybe 12 or 24, inside a loose tube. And in general, the tensile strength members we use today are soft and flexible, so they are typically cut short at the termination enclosure at the entrance. So you have 1 to 5 meters of buffered fiber outside of that termination, and you don't want to have any damage from stripping the jacket or from pinching them, kinking them, etc., causing problems. And we strip in a variety of materials. For years, you had rubber and PVC electrical cables that you were stripping, maybe polyethylene telephone cables. We use a variety of different plastics today, including low-smoke zero halogens, which are many times highly filled, flame retardant materials, PVDF, which is a form of fluoropolymer. They all have different characteristics, but we also strip other things in our cables. We strip corrugated steel armor, if you will, the conventional rodent protection for both copper and fiber cables. And this is typically 6,000ths of an inch or 0.152 millimeters in thickness, and it's coated on both sides with an adhesive material that sticks it to the polyethylene outer jacket. Now you're thinking about this. You're taking a yarn and you're cutting through steel. You're asking the yarn to do an awful lot for you as a ripcord. So we have to think about how we do it and how is the yarn designed to do this relatively unique task. When I talk to folks outside the fiber and the cable industry as a whole and talk about peeling armor with a ripcord, they always give me that very strange review of, you're kidding, right? And the answer is no, I'm not. Now, a new class of jacket is the non-metallic rodent and insect-resistant polymers. These are very hard materials, typically a nylon type 12 or something similar. That's very hard that the rodents can't get their teeth into. This is basically the demand for cables that are non-metallic but are termite or rodent resistant. And these materials are very, very resilient to this kind of behavior. So this is what we strip. We're stripping a lot of different materials from years ago when it was just a soft polyethylene or PVC or rubber jacket. Now let's talk about indoor cables, some of the failure modes. And there's terms here that probably some of you may recognize, some of you may not. I refer to one of these as turtlenecking. If you think of a turtleneck shirt, how it bundles back, or a turtle's neck, how it folds and the skin sort of collapses. If you have a simplex or even a 12-fiber cable with a fairly thin jacket, and you were to use one of the yarns as a ripcord, as you'll see in the picture on the right here, this is the same cable before being pulled. This is the cable where you've grabbed the strength member, the in this case a yarn, and you've grabbed the remaining yarns and the buffered fiber and pulled. And you can see how the jacket, because it's not bonded to these strength members, actually pushes back. And this area right here, where it's crinkled up, is also pulling back the optical fiber, the buffered optical fiber, and causing it to macro bend through this area. And while you can pull it back out afterwards, you may, depending on the hardness of the buffer and the particular design of the buffer, cause permanent attenuation increase or a sensitivity to increase in the future as the cable ages. So what do? We call this turtlenecking. We also have bending below the minimum radius. When you're pulling it, literally will pull almost a 90-degree bend. And you may actually exceed the minimum bend radius of the fiber, which also will shorten its life. You may not break the fiber, but you may shorten its life quite a bit. The same is true with increasing shrink back by compressing the fiber into this condition, this high macro bend condition. It's not always a good choice. So beyond materials, then, what makes for a good ripcord? Well, we have to design for the applications, and we'll talk more about this at the end when I break down a little bit of the other problems that are related to ripcords, not so much as how they work, but the problems they can create for the cable designer trying to pass a specification. One is the design for the applications. Flat ripcords material may be used in certain applications where the jacket is soft. That one you just saw was a good example. The previous slide right here, this is a soft jacket, so a flat or untwisted ripcord will work quite well. But sometimes you have to braid it or reinforce it when you need it for heavier, like cutting through steel armor or the non-metallic armors that are used for termite and rodent-resistant cables, as well as the temperature range. If you use a material that, say, softens at high temperature, it may not work as a ripcord. You may want something that is basically a thermoset material, like an aramid or a fiberglass. And, of course, the other side of this, there are coatings that are appropriate now for these ripcords. In some cases, the material that's used as a lubricant, this lubricant is almost like a wax to help, if you will, yarns tear through steel armor and not destroy themselves in the process. Other cases, the cables, one of the other problems is they have to not let water pass, so they have to have a water-swellable component. We also don't like our cables to create bacteria and mold resistance. For years, that wasn't considered a major issue. But as you've seen in flooding and so forth, the bacteria and mold cause a number of secondary issues downstream that can be major problems. So it becomes much more important. We'll talk a little bit more about, we talk about standard loose tube cable failures, central core bundled fibers and ribbons. In many cases, we would score loose tubes. And that occurs when you are trying to cut the jacket off, or if you're not using a ripcord, you're just slicing it to get where you need to be. And you can slice a loose tube, the ribbon matrix material, or even the fiber optic coatings on the fibers. And if a ripcord, when it breaks, causes someone to create a new start, they take the knife, they wring the cable trying to get to the ripcord again, and they will typically score the cable. This is a good example of cutting blade damage when restarting a ripcord. These are standard 12-fiber loose tubes. They're dry core, so you can see these are the, if you will, the modern ones today. The picture in the center shows a very mild scrape. This is just approximately 12 to 15% through the standard loose tube. This picture on the left is through about 50, 55% of the wall of the loose tube. That 12%, when it was bent, as you would bend it in a splice case or into any kind of frame, literally will break open. You're now exposing the coated optical fibers to the atmosphere, to the outside world, and to damage that you didn't plan on. Plus, your bend radius of the tube is no longer intact, and you can create a tight tolerance bend radius there. So the issues of why it doesn't work, we have to figure out, what do we tell the installers? Our present specification says strip by following the manufacturer's recommendations. And usually these are on the manufacturer's website and rarely accessed in the field. In most cases, they are going to rely on tribal knowledge. This is what Joe, who taught me how to install cable, told me 10 years ago. That's the primary source. When you spend time with installers, you hear that more and more. I learned this from so-and-so who taught me, who was the senior guy on that job that I learned how to put fiber cable in. So we hear this over and over again. And tribal knowledge, what does it tell us? That basically the methods that we're taught may not always adapt to our current cable designs. We've improved cables. Early cables were pretty solid for outdoor use. They were gel-filled, gel-flooded, not gel, but actually a relatively thick material flooded, and there was no real open space in them. So they felt like a power cable, if you will. Those tools won't work so well on modern cables that have a lot less material and a lot more fiber in them. The other thing is that sharp edges on the gripping tools are going to shear the fiberglass or weaken the aramid or nylon ripcords. And how do we pull it? Do we pull at 90 degrees, which is the natural reaction, or at 180 degrees, which allows you to maintain the bend radius of the fiber? So here's an example. On the right side, on the left side, you'll see that the ripcord is being pulled by a pair of pliers. They're grabbing it, squeezing it. You've got sharp edges. The odds are that that will tear before it will pull through that armored armored cable. Second one, you've taken a pair of point nose pliers. You've grabbed it in the center, wrapped the ripcord around the rounded edges of the pliers, and you're pulling at 180 degrees, and it will do a pretty decent job of tearing through that steel armor. Another issue is when we're dealing with armor, we typically use two ripcords to banana peel it. And I'll show you that in a second. That's the next slide. But here you'll see two ripcords that are placed very, very close together. So when they peel, they will go through the same slot. You're only going to get one slot. Now you're fighting to open up steel armor. Doesn't really work. And this is a good example of a correctly slit steel armor cable. You can see the armor on the inside here, one ripcord on the top and on the bottom, and that's what we refer to as a banana peel. If you have two ripcords close together, you've got it on one side, and you're now trying to peel this apart by hand. That's a pretty hard thing to do. So we don't want to do that. And then ripcord construction, fiberglass, twisted fiberglass, aramid yarns, nylon yarns, twisted nylon and aramid yarns. They come in a variety of different materials. This is just a typical company that makes the ripcord materials and constructions. You can see their options that are here. Different materials, polyester, Kevlar, which is a trademark from DuPont, Vectran, which is also a trademark name. Break strengths are relatively high, but it's not so much break, it's the wear strength. And they talk about what they've added, lubricated or water repellency coatings or utilize to eliminate outgassing, non-wick coatings. Water can't get through. And, we talk about these things like water and so forth. Why is that important? That has to do with the design of the cable by the end user. So, we're getting to that point. What are we looking for? We've talked about this before, the lubricants, the water swivel, the mold, and so forth. So the next question is, for a manufacturer, what can go wrong besides this? Well, if you have a really strong ripcord, if you put the heavy ripcord in, like you see here, you may actually reach the point where the jacket minimum point specification isn't met, and you're adding more plastic around the entire cable in order to meet your min spec. Or you're failing because you don't have you're not meeting the min spec because the material will not compress enough to make it thin enough. In addition, mechanically, this can cause problems in the field. With a hot day, the cable might literally slit open at that point if the jacket is thin enough. And we are making them thinner than we used to in order to fit more cables into a conduit. If the material isn't stable at temperature, it may not work in a hot day. Another problem is these cables have to pass a water blocking spec, and whether it's fresh or salt water, the ripcord being especially a braided or a yarn will generally wick water. And you add material, but do you add fresh or salt water? And how well will the ripcord work if it has been activated by water because you were installing it in a rainstorm? These are all questions for the manufacturer, if you will. So considerations. You need to match ripcord tenacity to the jacket design and material. And you got to recognize all the other requirements, such as min point, thickness of the jacket, whether or not it's got to have fungus and mold resistance. And we have a great opportunity for improving the generic stripping and procedures that we have out there today. There really are no good procedures out there. Each manufacturer has a great video, but there's nothing that's taught as a generic stripping procedure. So there's a lot of different requirements in copper cable, and there's new and emerging designs that are going to continually push us to design and engineer the ripcord instead of add it. And we have a good opportunity, I think, to develop more complete specifications and test procedures specifically to help train the next generation of installers. And we really do need to classify ripcords by type of jacket. And with that, I'll turn this back over to Ed. Thank you for your attention.
And excuse me, and thank you, Wayne. At this time, we'll ask as many questions coming from the attendees as time permits, starting with this first one. Are ripcords used in the splicing and or connectorization process for fiber optic cables? If so, are there recommendations on how much jacket should be peeled back, like copper cables?
In general, they are used in splicing and also in midsection access. And the amount that has to be peeled back is determined by the type of splice enclosure they're being put into. For example, a typical underground or aerial splice enclosure that's going to be fusion spliced, they're going to want 5 meters of buffer tube and fiber coiled up inside there so that they can exit the buffer tubes or the fibers to a fusion splicer, or fiber ribbons to a fusion splicer. In other cases where you're putting a termination on, say, frication tube and connectors, depending on the particular size of the patch panel they're going to, that may be 1 meter or less. So the sizes vary tremendously based upon the particulars of the end user's application and the splice case or termination method they're using.
Okay, thank you. Next question. Are fiber optic ripcords only used for outer jackets, or are multiple ripcords used in cables with subunits?
It depends on the design of the cable. In some cases, very large cables that have relatively strong subcables will have a ripcord in them, or they'll have parallel strength members that could be used as a ripcord. But generally, the outer, if you have a layer of steel armor and then an inner jacket of polyethylene under the armor, as in some of the more traditional designs, there would be a ripcord under each individual jacket. So, for example, the outer jacket and armor would have what's commonly referred to as a braided or twisted ripcord of aramid or nylon, something relatively strong with appropriate coatings to peel through the armor. Then there might be a flat aramid or nylon or fiberglass ripcord under the inner polyethylene jacket that's thinner, but acts as just a layer between the optical core and the steel armor. Many of the newest designs no longer incorporate that extra layer of polyethylene. That goes back to some of the very first statements I made about the fact that we're trying to reduce the cost of fiber optic cables, and we're now looking at a half a cent or 1 cent a meter as a major cost reduction. And so therefore, if you're looking at these cables, that particular portion is dealing with what I would call traditional or orthodox cable designs.
Okay, thank you. Next, are stripping methods different from manufacturer to manufacturer and or material to material?
Typically, the manufacturers all try and give you the best practices which are similar. Some manufacturers have more detail out there in terms of videos online or more literature, but in general, most manufacturers recommend the same procedures, pulling at 180 degrees, taking a short area, rounded edges to pull with, and particular indoor cables or special designs may have different instructions from manufacturer to manufacturer. And as to materials, it'll vary based upon the type of design and how the ripcord was engineered into it. Typically, armored cables, you're going to see the fact that you don't want to pull it by hand. You're going to want to pull it with a tool, which could be nothing more than a broomstick handle that you wrap the ripcord around and pull back along as where on a soft cable, you may want to just, the procedure may say you're going to lay it on a flat table, wrap it around the point nose pliers as an example, and pull straight at 180 degrees.
Okay, thank you. Next question. What would direct the designer to use a high-tech ripcord yarn such as an aramid or LCP instead of polyester or nylon?
Two things. One would be performance over temperature range. Nylon or polyester might be much more sensitive to deteriorating in a hot environment. Typically, outdoor cable jackets are made with carbon black and are a very good absorber of sunlight. And if you've ever been on a cable installation site where they've figure-eighted the cable out on blacktop prior to pulling it into the ground and then are going to strip the ends, you know that the jacket is almost softening. The polyethylene is almost getting soft. But that also means that the ripcord underneath is getting soft, and therefore its tenacity will change over temperature. Aramid yarns, in particular, are known to be extremely stable over very, very broad ranges of temperature in terms of tenacity and strength, so they will be pretty much unaffected by most terrestrial temperatures that you would run into. But as I say, if you've ever been into a job site in the summer, let's say even in the south part of the U.S., and they figure-eight the cable on a canvas on top of a blacktop, you don't want to handle that cable without gloves. So it gets pretty warm, and you want to make sure that the ripcord will work for the installation temperature range. In some cases, that temperature range may only be 80 degrees Fahrenheit, but the cable, because of sitting in the sunlight, might be at 110 or 115 degrees, which means that that ripcord is also at that higher temperature. But the countervailing situation is the jacket may have softened a little bit too. But as we go to more high-tech jackets, high-density polyethylenes and other materials, it may not, the difference may not be successful. That's where coming up with new methods testing ripcords becomes an important consideration. That's an opportunity the industry as a whole has, is to update some of those procedures.
Okay, thank you. Next. The submitter is saying this: we replaced light aramid ripcords, 3 tiers, with much heavier aramid ripcords, 4 tiers, for the armored optical cables. The ripcords still broke in some cases. Looks like heavier ripcord did not help at all. Do you have any suggestions on this?
Yes. Typically, I think tiers, he's referring to yarns or bundles, if you will. And my reaction would be that they were putting them in and they were not braiding them or stranding them in some fashion or twisting them. The second one, as I mentioned earlier, is when you're cutting through steel, you want to have a lubricant in that ripcord to help it cut through there. The lubricant could be something like a wax, and I use wax as a generic example. There are many companies that will produce ripcords with lubricants that are proprietary to them, and I can't define those. But working with companies that make ripcords, there are wonderful solutions out there to make the aramid yarns really perform extremely well through very, very impressive corrugated steel armor. The other item is making sure that you're using the correct technique, as I said before, of winding it around a rounded edge and pulling at 180 degrees instead of at 90 degrees. So we have to check the procedures of how you strip, whether or not the yarn is lubricated, and whether or not it's parallel yarns or stranded or bundled or twisted yarns.
Okay. Thank you, Wayne. At this time, I am seeing no further questions, so I would like to thank you, Wayne, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Wayne after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, August 16th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader, showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019, at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 17th through Thursday, March 19th, 2020 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us with your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.